Okay, so we're continuing in 6.3. We're working with the Heaviside function, and I thought we would just do a few computations. So let's continue with this example that we were working on when we stopped here. In the last video, we showed that the Laplace transform of u sub c of t times f of t minus c is equal to e to the minus cs f of s. And so we want to use this to find the Laplace transform. Use the table to compute the Laplace transform of u sub 3 of t times t squared. So if we look at our table entry here, I see that t squared needs to be f of t minus 3, right? So let's make a note of that. We need f of t minus 3 to be equal to t squared. And now the second thing to notice is that this is not the Laplace transform of f of t minus 3, right? This is the Laplace transform of f of t. And so I don't know what f of t is. I only know what f of t minus 3 is right now. So that is my next job here. If this is f of t minus 3, then f of t must be, we're kind of going backwards here, wherever I see a t in this expression, which is right here, I'm going to replace that by a t plus 3, so that's going to be t plus 3 squared. And notice now, to go back, if I wanted to go backwards, right, I would replace t by t minus 3, and I would get back to t squared again. Okay, so the upshot here is that when you're trying to find your f of t, you can replace your t by t plus c, and that should get you what you need. Okay, and so now if I'm taking the Laplace transform of this, I need to go ahead and multiply it out. Okay, and so that gives me my f of s. Again, we're using the table. That's going to be 2 over s cubed plus 6 times 1 over s squared plus 9 times 1 over s. Okay, and so therefore the Laplace transform of u sub 3 of t times t squared is equal to e to the minus 3s times our f of s. So 2 plus, I'm going to go ahead and write that as 6s plus 9s squared, all divided by s cubed. Sometimes that's a nice way to write that. Very good. You don't have to write it that way, but that is a nice way to do that. All right. So this is, again, this was an example showing you how to use this table entry. This can be kind of tricky, so you might take a look at this example one more time. Okay, now let's try to use the Laplace transform to solve a differential equation. So how about if we try to solve y double prime plus 4y is equal to f of t, where f of t is equal to t if 0 less than or equal to t less than 2, and then it's going to be 2 after that. Okay, so it looks like we're going to have to go ahead and rewrite this. Oh, I'm going to use 0 initial conditions as well. Okay. So first off, let's figure out what f of t is in terms of our Heaviside functions. So, whoops, in terms of our Heaviside, f of t is equal to the function t, and that's going to be u sub 0 of t minus u sub 2 of t, that's our on-off switch, plus 2 times, and now we just have an on switch. And at this point I just wanted to make a note about this u sub 0 of t. U sub 0 of t, if you take a quick sketch here, u sub 0 of t is just u of t, and so that's 0 for t negative and 1 if t is positive. But in terms of the Laplace transform only works with positive time. And so therefore, u sub 0 is just identically equal to 1 in terms of a Laplace transform. And so often our book will replace u sub 0 by the function 1, and you can do it either way. I'll go ahead and do it in this case just for practice here. Okay, and now I'm kind of anticipating needing to take the Laplace transform, so let's simplify this. So that's going to be minus t u sub 2 plus 2 u sub 2, and you can abbreviate your Heavisides this way if you'd like. And I see something nice here. If I take a minus out, that'll be t minus 2 u sub 2. Notice I'm thinking of the u sub c of t, f of t minus c, kind of in the back of my mind. Okay, good. And now I think we are ready to take the Laplace transform of both sides of our equation. So apply L to the OD, and we get, do you remember what the formula is? S squared y minus s y of 0 minus y prime of 0. Of course, in this case, both of those are 0, plus 4 times y equals, now the Laplace transform of this side is just going to be 1 over s squared minus e to the minus 2s times 1 over s squared, right? Excuse me. And so, yeah, this turns out to be nice when you already have the right form. Good. So let's simplify. I get s squared plus 4 times y equals 1 minus e to the minus 2s. Whoops. 2s divided by s squared. Good. Then y is equal to 1 minus e to the minus 2s divided by s squared times s squared plus 4. And now, how are we going to work with this? We're going to rewrite y as 1 over s squared times s squared plus 4 plus, minus e to the minus 2s times 1 over s squared plus, darn it, s squared plus 4. Okay. Now, I'm going to go ahead and invert this, but I see that this is appearing in both of these, right? And so let's go ahead and just work with this quantity. So let h of s be equal to 1 over s squared times s squared plus 4. And then notice what's going to happen, right, when I take my inverse Laplace transform. If we can solve for h of t, right, the inverse of that, then I can write down my solution. Y of t is going to be h of t and then minus u sub 2 of t times h of t minus 2. So then this whole problem just reduces to inverting h of s. Good. Now, how am I going to invert h of s? Partial fractions, did you say that? So let's see if we remember how to do partial fractions with this kind of a form. Whoops, sorry about that. So h of s, oh, let me write it differently. I'll just go ahead and take it. 1 over s squared times s squared plus 4 is equal to a over s plus b over s squared plus cs plus d divided by s squared plus 4. Right? Clear the fractions on both sides, and you get 1 is equal to as s squared plus 4 plus b s squared plus 4 plus cs plus d times s squared, right? And so 1 is equal to as cubed plus 4as plus bs squared plus 4b, hang on, plus cs cubed plus ds squared. It's not as bad as it looks, although we're running out of time. I think we're going to stop here. We're at the 10-minute mark, so I'm going to continue this in the next video.